Hello everyone, welcome to this video. In this video, we will discuss the different operating conditions of a three-phase power system with normal and different fault conditions. So we need to see the symmetrical and asymmetrical faults, different types of faults, and we need to see how the symmetrical components will be in these different conditions. So here the system, I already built it in Simulink. And I will go through all these elements in order to make sure that it's clear. First of all, you need to go and let's say include Power GUI in your project, and it will be continuous by default. So what you need to do is to select phasor, and then you need to select the frequency of the power system. In this example, the frequency of the power system is 6. So you need to make sure that you start with this block, because having this block in phasor format will allow you to select different, let's say, options for the measuring equipment. So we will discuss them a little bit later. So let's start with this Power GUI. After that, I installed a three-phase system. So three-phase system can be, or three-phase source can be, let's say, built from three single phase sources, or a three-phase system. So here I'm using three single phase sources. So what I'm using AC voltage source. So for phase A, I'm selecting the peak magnitude to be 10 volts. I'm selecting the phase angle for A to be 0 and the frequency to be 60 hertz. So of course, you can select any values for the magnitude voltage. Here, I'm just presenting 10 volts in order to make the numbers, let's say, clear, and we can, let's say, elaborate them without going and using the calculator. So this is for phase A. So phase B will be the same, with one exception, is that the phase angle will be at negative 120 degrees. For phase C will be the same, 10 in magnitude, hertz is the frequency, but here is the phase is positive 120 degrees. So this will make a three-phase system, balanced three-phase system with equal magnitude, and the three phases are displaced by 120 degrees from each other. So, and phase B lags phase A, and phase C leads phase A, which means that we have a positive sequence. So the neutral point of this three-phase source is grounded. And as you see here, I have a solid ground because I don't have any impedance in the neutral connection. Here I'm using a current measurement device. So this is current measurement device. So I'm using it to measure the current in the neutral connection. And we know that the current in the neutral connection should be equal to 0 if the system is balanced and we have, let's say, balanced conditions. So I'm selecting to show the complex number. So here you have complex real imaginary magnitude, or the magnitude angle and magnitude. So I'm selecting the complex format. So apply and OK. So this will be I neutral in ampere. So this will be shown on this display. So now I'm connecting each phase in series with a reactors. So this reactance will, let's say, play the role, the transmission line or transformer plus transmission line. So something like this. So these reactances, I selected them to be J0.377 ohms. So this reactance is given in ohms. So if you do double click, so what I'm using series RLC branch. So I'm selecting the branch to be only inductance. And here I'm using this inductance to be 1 millihenry. So if you multiply 1 millihenry by 2 by F, where F is 60 hertz, it will be 0.377 ohm. So this is for this inductor, and it's the same for this one. It's the same for this one. So you just set it for one, and then you copy paste for the other phases. And here I'm using again a current measurement. In this current measurement, I'm measuring the current in phase. And of course, in symmetrical conditions, it will be the same current in phase B and phase C, but displayed by 120 degrees from each other. So I want just to observe current in phase A. Of course, if you want to observe all currents, you can add the other current measurement devices. And here I'm also using a voltage measurement device. So this voltage measurement device is connected between phase A and the ground. So it will be phase to ground, phase to neutral, or phase to ground, or line to ground, or line to neutral voltage. And I'm selecting for this voltage measurement magnitude and magnitude and angle. So I will have, this is normal display, but you expand it in order to see the two numbers. This number will be the magnitude, this number will be the angle. For this current measurement device, I selected complex format. In complex format will show you the real part and the imaginary part. So it will show you the complex value in rectangular form. So it will be current or voltage, whatever. Here we have current, so it will be in rectangular form. So when you select complex, it will be in rectangular form. And here I'm using a three-phase volt ampere measurement device. So for this three-phase volt ampere measurement device, I'm selecting the phase to ground voltages. So these are the voltages phase to ground, phase voltages, phase to ground or phase to neutral, since the ground is connected to the neutral, so it will be ground. And then I'm selecting also currents to measure, and these, of course, the line currents. And again, I'm selecting the complex format, selected complex format. So what I have here, I will have the line currents in complex format. So this current in phase A should match this current. And here phase B, phase C. And again, as I told you that this is a display, the normal display that we are using, just you need to expand it so you can see all the numbers that you want to see. And here we have the phase voltages. The phase voltages also measured. So this voltage, as you see, it should match the voltage in phase A because this is the same voltage. This is the voltage in phase B. This is the voltage in phase C. Okay, and this system is connected to a three-phase RLC branch. So this is a three-phase series RLC branch. So I'm selecting it to be pure resistive, and its value is, as you see here. So let me see how many zeros we have. 1, 2, 3, 4, 5, 6. So I have 1 mega ohm. So just in order to do the simulation, so I'm not, let's say, simulating a normal current, but of course, if I leave it open circuit, MATLAB Simulink will not accept it. So I need to have some value which is large to simulate something near to the open circuit. And here, as you see, I have again a ground. So this load is connected in Y, and it's connected to ground. Now I have here a new block also, which is symmetrical components. A block for this is for voltages because the input signal is the voltages from ABC, and then it will show you the positive, negative, and zero sequences. So this will be the positive, this will be the negative, and this will be the zero sequence. So in the same order as it is shown here. So it will be the voltage, positive, negative, and zero sequence components. Again, here I have the same block. So let's see what is the name of this block. So the name of this block is Symmetrical Components Transform. Symmetrical Components Transform. And we are using the four-disk transformation. So this block implements a symmetrical components transformation when the power invariant option is off. So when this is off and checked, so the block implements the four-disk transformation. So this is the one that we are using. It's the same one as here. So here the input are the currents. So we see the components of the currents, I positive sequence, I negative sequence, and I zero sequence. Again, I'm selecting here. So here by default, it will show you in a complex format. So it will give you a rectangular, complex and rectangular format. So, and here I have some formulas to just recall what formulas we are dealing with. So the voltage in any phase, so in phase A, it will be VA1 plus VA2 plus VA0. And we know that these symmetrical components are for phase A. And we know that IA, which is this current measured here or measured here, it will be the sum of the three components IA1, IA2, IA0. And we know from KVL for symmetrical network, different symmetrical network, that VA1 is equal to VF minus IA1Z1, VA2 is equal to negative IA2Z2, and VA0 is equal to negative IA0Z0. And of course, it is Z0 plus 3 times the neutral, that we don't have it in this model. So this is why I'm not indicating it here. Okay. So I went through all these components. So again, these are simple displays, but you expanded. So this is a display. So I'm selecting format bank in order to see only 2 digits after this decimal points. And this is more than enough in terms of viewing the numbers. So I don't need to have more numbers. So of course, if you select other than band, for example, short or long, so you will see a lot of, let's say, numbers or in terms of scientific notation, and this will be inconvenient to elaborate on, let's say, without the use of a calculator. Okay. So now this is what we have. So let's run the circuit. I'm selecting the simulation time to be only 1 second. So I do run the circuit, and here we have the circuit. Since we have a large amount of resistance, so this, let's say, condition looks like to be an open circuit condition. Open circuit condition. So I see the voltage in phase A is 10 into 0 degrees. I see the voltage in phase A here is the same one here. I see the voltage here is negative uh, uh, 5 plus J 8.66, the magnitude of which is 10. So this is again magnitude 10, but it displays by 120 degrees. And this is for phase C. It's also has the magnitude of 10, but displaced by 120 degrees. I see all the currents in all phases equal to 0 because I have a very large amount of resistance, 1 mega ohm, that will simulate an open circuit. So since this is a symmetrical condition, so we don't have any asymmetry. So what we see that the voltage, we have only positive sequence voltage. And if you add the positive sequence voltage for phase A plus the negative one plus the 0, 1, you will see that it is equal exactly to the voltage that we have for phase. For the currents, the sum of the symmetrical sequence components of the current will be the current itself, and the current is 0, and the sum of all symmetrical components is equal to 0. Okay, now I want to simulate, let's say, having some load. So for example, I will say that this resistance is equal to, let's say, 10 uh, ohms, which is some load, okay? Instead of 1 mega ohm, now it is 10 ohm. I do okay, and then I will run the circuit again. So what I see that we have a current here up here, and this current is 1 minus J 0.04. So we see that the real component is dominant here. Why is that? Because the circuit is resistive. Here we have 1 ohm, while here we have only 0.377 ohm. So it's a more resistive circuit. Of course, it's inductive resistive, but it's more resistive because the resistance here is greater than the inductance in this circuit. Here we see the three currents. Again, if you calculate the magnitude, you will see that they will have, sorry, the voltages, they will have the same magnitude. We see that here is not 10 anymore because we have some voltage drop, a slight voltage drop on this reactance due to the flow of this current, but it's still close to 10, still close to 10. And this is VB, VC, and they are displaced by 120 degrees. So these are the currents with line A, line B, line C. They will have the same magnitude and displaced by 120 degrees. For symmetrical components, since the system is still balanced, so we see that the entire voltage in phase A is a positive sequence component. Negative sequence component is equal to zero. Zero sequence component is equal to zero because the system is still balanced. And when the system is balanced, normal operating conditions, everything would be only positive sequence. And similarly for the current, I see that the current here is the same line current here, no negative sequence, no zero sequence, only positive sequence, and positive sequence is equal to the current itself. So negative sequence is equal to zero and zero sequence is equal to zero. And this is valid in symmetrical conditions, no matter it is normal conditions or open circuit or normal load conditions, or even three-phase short circuit, three-phase short circuit or any symmetrical fault. We see that the current through the neutral is equal to zero, and because we have three currents equal in magnitude displaced by 120 degrees from each other, so their sum will be equal to zero. Their sum equal to zero, so we don't have any neutral current. Okay, now I want to simulate a three-phase short circuit. And for three-phase short circuit, and this resistance should be equal to zero, but since MATLAB will not accept zero, so let's assume that we have such a small value, okay? And I will do apply and okay. So now the resistance is a very small, it will be ignored. So we have three-phase short circuit. So let me run the circuit and here it is. So what we see first that the voltages, the three voltages at the fault location is equal to zero because all the three-phase voltages are short-circuited. They are also connected to the ground and the potential of the ground is zero. So we see the voltages at the fault location is equal to zero. But still we see the voltage at the source is there. So we have 10 volts in each voltage source and displaced by 120 degrees from each other. Here is the fault current. The fault current is a negative J 26.53 amperes. So this is the fault current, and the fault current will be calculated as this voltage source divided by this reactance. We ignore this small value, so it will be divided by this reactance. So if you divide 10 by 0.377, so it will be 26. Since we have J here, J goes up as a negative J. So here we have the fault current, the fault current. Okay, so let's have a look at the, let's say, three other phases. So here is in phase A, and here is in phase B, and in phase C as well. So if you, let's say, calculate the magnitude, you will see that the magnitude is again 26. So these three currents are equal in magnitude and displaced by 120 degrees from each other. If we look at the symmetrical components of the voltage, so since all of them are zeros, so since we have a symmetrical, let's say, fault conditions, then we don't have any negative or zero sequence. And since the voltage at the fault location is equal to zero, the positive sequence of the voltage is equal to zero. Here is a little bit different. So here we have the fault current in phase A, and we see that the fault current in phase A is entirely equal to the positive sequence component. No negative sequence component, no zero sequence component, because the type of the fault is symmetrical, which is a three-phase fault. Again, because we have symmetrical fault, so we don't have any current in the neutral connection. Okay, so let me now return the resistor to be 1 mega ohm. 1, 2, 3. 4, 5, 6. Okay, I will apply it. I will do okay. Run the circuit to make sure that it's correct. Yes, it is correct. So we see that the current is back to zero. Voltages are normal. 10 into 0, 10 into negative 20, and 10 into a positive 20 degrees. Okay. So what I want to do now, I want to simulate a single line to ground fault. So what I need to do, I need to copy this ground. So I will copy it and I will paste it here. So this is the ground that I will be using to simulate the single line to ground fault. So I will delete this line, then I will connect A to this ground, okay? And then I want to connect it to the load itself, back to the load. Okay, so what I have here, I have phase A grounded. So it's a single phase to line ground. So this should simulate a single phase to line ground, and the phase that has this fault is phase A. Phase A, while phase B and phase C are healthy phases. Okay, now I want to run the circuit once again, and let's see what we have. So again, for the voltage at the source, they are normal 10 in magnitude, and they are displaced by 120 degrees from each other. When it comes to the voltage at the fault location, so we see the voltage at phase A is equal to 0. For phase B, for phase C, which are healthy phases, are still 10 into negative 120 and 10 into positive 120 degrees. So they are still healthy phases. The currents in phase B and phase C, we don't see any currents because we still have large impedance here, 1 mega ohm. So phase B and phase C are let's say, considered to be still open circuited. So I don't see these currents. While here I see the single line to ground fault current for phase A that is going through ground and back home, back home to this source. So how much is this current? Is negative J is 26.53. So this will be the current in single phase to ground fault. And I see that it is the same value in ion neutral. You see, this is the same current in ion neutral. So a single line to ground fault goes like this. Okay. Now for the voltage at phase A is equal to 0, then this means that according to this formula, that the sum of all symmetrical components should be equal to 0. So let's do the sum. So for the imaginary part, I see that it is 0, so the sum of the imaginary part is equal to 0. So let's have a look at the real part. So real part for positive sequence is 6.67, negative sequence negative 3.33, zero sequence negative 3.33. The sum is equal to 0, then VA is 0, and this formula is valid. So for this current, I need to see whether this formula is valid or not. So the sum of the symmetrical components should give me this current, which is this current, and which is this current. Okay, so let's do the sum. So I see the real parts are all zeros. So the sum of the real parts would be 0, and here it is 0, 0, and 0. So let's see the imaginary part. So the imaginary part, I see that in each phase, in each symmetrical component, it's 8.84. So negative 8.84 times 3, it will be 26.53. Negative 26.53. So I see that the sum of the symmetrical components of the current is also equal to IA, and thus this formula is valid. This formula is valid. And again, if you verify for this these symmetrical components of the voltages, you will see that they are valid. That they are valid. Okay, so what we need to do now, I need to simulate the line-to-line fault or double line to ground fault first. Okay, so let me go to the double line to ground fault. So let me delete this line. Let me see whether I can connect this line with this point. Yes. And I want to delete, complete this. Then I want to delete this line. Okay, so I want to do double line to ground fault in phase in two phases B and C. Okay, that's great. So what I did, I connected phase B to phase C, and both I connected them to ground. Okay, now I will run the circuit, and this will be double line to ground, two lines and the ground. Okay, so let's see what we have here. First of all, I see that the voltages at the source side are the same, which are magnitude is 10, angles are displaced by 120 degrees from each other. I see the current in phase A is equal to 0 because it is open circuited. Here we have a high resistance, which is 1 mega ohm. Phase A is healthy. We don't have any fault in it. So the current is equal to 0. Since the current is equal to 0, I see that the voltage is the same voltage here at the source because I don't have any voltage drop across the line. So for the other phases, phase B and phase C, I see that the voltages are 0 because they are short-circuited and grounded. So they are equal to each other and grounded. So they can be other than 0, a very small number other than 0, if you have some kind of Z neutral before this ground. Okay, now let's see the current. So I don't see current A because A is in open circuit, but I see a large current in both phases B and C. So on both phases B and C, and this is the current of phase B, this is the current of phase C, and their sum will be the fault current. So this the fault current, and this will be their sum. So if I add these numbers, so the real part will sum to 0. Here it's the 0, and the imaginary part will sum to a positive J26.54, and here is J positive J26.53. Here it's 52. Yes, here 53. Okay, so it's the same number. So I see that the fault current is the sum of both IB and IC. So let's have a look at the symmetrical components. So we have phase A, and these are the symmetrical components for phase A. So these symmetrical components, the sum of them should be exactly as phase A. So if I sum of them, I see that the imaginary part is equal to 0, imaginary part is 0, the real part of all sequences, positive, negative, and 0, is the sum of it is 10. And here we have 10. For the current, so I see that IA is equal to 0. These are the symmetrical components of the IA. So if I add them up, it should give me 0 according to this formula. So for the real part, it's 0, and here we have 0. For the imaginary part, so negative 17.68 plus 8.84 plus 18.84. So it will give me 0 as well. And here we have it. 0. If you apply, if you add the 0 sequence component plus A square, the positive sequence component plus A times the negative sequence component, you will get IB, and then you can use also same and it's a relationship to find IC, but you need to add the 0 sequence and multiply A by the positive sequence and A square by the negative sequence. So I see that this what will be for the line to double line to ground fault. And the last, let's say, condition that I want to simulate here is the double line to line fault, line to line fault. So what I'm doing now, I have a short circuit between phases B and C. A is still healthy phase, large resistance, so it will be open circuit for phase A. But I see that phase B and phase C are short circuited. And I will run the system again. Again, what I see the voltage is still of the source 10 into 0. Here we'll have 10 into negative 20 and 10 into positive 20. I see that the neutral current is equal to 0 because I don't have any fault that is related to the ground. So what happens, there is no current in phase A because it is open circuited. We have a large value of resistance here. The current in phase B will flow this way and go back through phase C, and for phase C, it's the same. The current will flow this way and go back to the source through phase B, through phase B. So this is let's say, the only loop that we will have that is composed of the two phases A and B. Ground is not involved here, ground is not involved, and the phase A is not involved as well. So as we see that we have fault current in phase B, fault current in phase C. So we see that they are the same current but opposite direction, because the current is flowing this way and come this way. So IB is equal to negative IC, and this is what is shown here. For voltages, we see that the voltage in phase A is equal to 10 into 0 degrees. We see the voltage is in other two phases where we have the fault. It is half of the healthy voltage, which is -5 and -5. So first of all, we see that the voltage is the same because B is connected to C, and we see that the voltage dropped to half, dropped by 5% if you have a fault uh, uh, between two lines, between two lines. Again, if we look at the symmetrical components, so these symmetrical components of the voltage, positive, negative, and zero, should sum up to phase A. So I see that 5 plus 0, 5 plus J0, 5 plus J0, and 0 plus J0 will sum up to 10 plus J0, which is correct. I see that I don't have zero sequence component, and here for the current as well, because the type of fault here, line to line fault, and in line to line fault, zero sequence component is not there. So we don't have zero sequence component in line to line fault. We don't have both zero sequence component and negative sequence component in three phase fault. So we have all sequence components in single line to ground fault and double line to ground fault. Okay, what we see also, if you add all these numbers, all symmetrical components, you should have IA. So 0 minus J13, 0 plus J13, 0 plus J0. So it will sum up to 0 minus to 0. So it will sum up to 0, which is the current in A. So in this, let's say, model, as you see, we saw the symmetrical components in different conditions, which are open circuit condition, load conditions, and three-phase fault, single line to ground fault, double line to ground fault, and line to line fault. If now I delete this component, let's say I deleted, so and you run the circuit, so now we are back to asymmetrical modes, open circuit. If I choose this value to be some value, assume that I have it to be 1 ohm, and apply OK. So we will see that this the normal operating conditions. And in normal operating conditions, we don't have neither negative or nor zero sequence components.